Next, we can look at the molecule butadiene. And we notice from the name that it must have a 4-carbon chain. That's where we get the buta part from. It has double bonds. That's why it's an ene, it's an alkene. And there are 2 such double bonds in the molecule. That is why it is a diene. And it turns out that there are 2 different conformations for butadiene. One we can draw this way. And we can add the associated hydrogen atoms. And we see in this particular conformation that relative to the central carbon-carbon bond, both of the double bonds are on the same side. Because they are on the same side, that makes this the cis isomer. Now that we've identified which isomer we have, we want to determine the point group symmetry for the molecule. If we look carefully, if we try to look in the plane of the board, for example, we see that there is no high order rotation axis greater than just the identity. But if we do look along this particular axis, I notice that if I flip the molecule over, that would send this carbon to that carbon, this carbon to this carbon, and all the hydrogens would switch places. So therefore, it tells us that we have a C2 rotational axis along this line. So the high order rotation axis for this cis isomer of butadiene is going to be a C2. Do we have any other interesting symmetry operations beyond the identity? Well, again, this molecule is completely planar, and that's a function of the double bonds. Even though we have a single bond in the center, it is conjugated with the double bonds, so that effectively each of the carbons here can be considered to be sp2 hybridized. Therefore, it's going to go to a trigonal planar arrangement. So this is going to be planar, so there's a plane in the plane of the board. Now we notice it's not perpendicular to the high order rotation axis. In fact, it includes it. So that tells us that this particular plane is a horizontal mirror. We also have a mirror along this plane here, and it reflects the lower left with the upper right of our molecule. So we have the identity, we have a C2, and we have 2 sigma V's. So that's a guarantee that we have a molecule that belongs to the point group C2V. Now we would like to assess the other conformation of butadiene. So let's redraw our molecule here. Again, this is going to give us a planar molecule, but now we notice that relative to the central carbon-carbon bond between carbons number 2 and number 3, that the double bonds are on opposite sides of this particular bond. Therefore, we have the trans isomer. So we want to look for the important symmetry operations for the trans isomer. If we start at the midpoint of the central carbon-carbon bond, we might, as we've been doing before, look for a rotational axis in the plane of the board, an axis that goes perpendicular to that plane. And we notice that we have such a rotational axis. The effect of this rotation would take this carbon to that carbon. The 1 and 4 carbons would interchange. The number 2 and number 3 carbons would interchange. And the hydrogens would line up with the previous position of hydrogen atoms, which tells us that in the plane of the board, if we rotate by 180 degrees, we have a C2 rotational axis. Do we have any other symmetry operations? Well, of course, we have the identity because we always have the identity. We also have a plane, a mirror plane in the plane of the board because this molecule is planar, again, due to the sp2 hybridization of the carbons. And we notice that this particular mirror plane is perpendicular, normal, to the high order rotation axis, which tells us that we have a horizontal mirror. So just from that information, the C2 plus the horizontal mirror, we know that this must belong to the point group C2H. Further confirmation of this fact we can get from looking for the one additional symmetry operation, which we know is present in C2H. We can tell from the character table, if we examine it for C2H, that there are 4 symmetry operations. And the 4th symmetry operation is inversion. And we notice that if we draw a vector from the central point to a carbon atom, for example, that if I go an identical distance in the opposite direction, I also arrive at a carbon atom, the identical type of atom. If I go from here to this carbon, in the opposite direction, there's going to be a carbon atom also. And I can do this for all the combinations of atoms in the molecule, and I will see that it all works. Which tells us that we have the inversion symmetry operation, and therefore we confirm that the trans isomer of butadiene belongs to the point group C2H. C2H. A very interesting and important molecule which seems to bear at least a little resemblance to ethylene is the compound diborane. And diborane has the chemical formula B2H6. And to show the similarity between diborane and ethylene, first I'd like to draw part of the molecule. So this is 6 of the atoms of the molecule. And we know that if I had simply replaced carbon with boron, I seem to have gotten at least a large part of the structure of diborane. The point at which the molecule begins to be different than ethylene is in the fact that in between these 2 boron atoms, I have 2 hydrogens. One of the hydrogens is going to be in front of the board. Try to draw this as a wedge. So this particular hydrogen atom is exactly between the 2 boron atoms, but it's above the plane of the board, which is a little difficult to draw. And then we also have a hydrogen atom that's behind the plane of the board, and it's directly behind this hydrogen. So the 2 green hydrogens are on this line. One's in front of the board, one is behind the board. And this gives us the structure of diborane. It has the peculiar structural element of a hydrogen atom that forms more than one bond apparently, and the hydrogen atom seems to be bridging. So this is a sort of a top view, a top-down view of the molecule. And then we can draw for perhaps a side view to kind of show more clearly what this molecule looks like. So on the side, we would notice that we have boron, boron. The bridging hydrogens are exactly in the same plane as each other and boron, and the boron atoms. And then the remainder of the 2 hydrogens, if I tip this up, this hydrogen will be in front of the board, that hydrogen will be behind. So the way that we denote that is by using our wedges. Hydrogen there. And on this side we have a hydrogen. So there would be this hydrogen, for example, would be in front, and then there'd be this hydrogen would be behind the board. So in our top depiction, we notice that 6 of the atoms are in one plane and 2 are not. And from the side view, we see 4 of the atoms in a plane and 4 of them not in a plane. So we like to determine the point group symmetry of this particular molecule. And the high order rotation axis we can find by going, well, one way to do it is through here, which in this particular, so this is for the top thing, this is going in the y direction, for example. Where that would be in this particular case would be between the things and coming up like this. So we have a C2 rotational axis there. We also have a C2 rotational axis in the plane of the board here. Okay. And we notice right away that the highest rotational axis that we can find in the molecule is going to be C2. And we've already found, and there's three of these, there's at least one C2 that is perpendicular to the other C2. In our bottom drawing, we can show that there's going to be a C2 along here, for example. And also, one coming out of the plane of the board. So if I rotate this way in the plane of the board, it'll take this boron into that boron, the front hydrogen and the front hydrogen, for example. Similarly, there would be a C2 axis perpendicular to the plane of the board. It would take this boron into that boron, this hydrogen into that hydrogen. So we have three mutually orthogonal C2 axes. And that, we recognize, is a situation that we have for a D2 group. So we see that diborane, at least so far, belongs to some sort of a D2 group. And the only question is, to which D2 group does it belong? And what we want to look for, the way we assess that, is to look for a mirror plane. And we can notice right away, particularly with this blue depiction of diborane, that there is a mirror plane in the plane of the board. 6 of the atoms of the molecule are already in the plane, and then we have a hydrogen directly in front and one directly behind that reflect into each other from the mirror. So this tells us that we have the point group D2H. So diborane, a molecule whose bonding is not easy to explain using conventional theories, has this D2H point group symmetry. When we have a completely linear molecule, our point group assignments become somewhat easier because there are only two possible point group assignments. One typical linear molecule that's considerable importance is carbon dioxide. So in carbon dioxide, we have 3 atoms that are all in a row. Now, if we were to look at this molecule down this axis, we would see is almost like an oxygen atom. We can consider the atom to be almost a sphere, but an incredibly small sphere. And one interesting feature of a circle, if we draw this perfectly as a circle, that if I rotate it by 180 degrees, it'll look the same. If I rotate it by 90 degrees, it'll look the same. But if I rotate it by any amount, 1 degree or 17 degrees or 35.6 degrees, it will look the same. In that case, we have a slightly different way of describing the rotational axis. So since I can rotate it by any number of degrees and a circle will still look the same, we have a symmetry element which we call the C infinity. So this is the one and only one case where the end value for a rotational axis is not an integer. So rather than being 1, 2, 3, we actually have infinity. And that corresponds to this idea of an atom as being a very small sphere, so to speak. From the end, it looks like a circle, and if we take a circle and rotate it by any amount, it's going to look exactly the same. So this is the condition. This is looking down this axis, for example. And we're looking down in this direction. So once we have this idea of a linear molecule, so all the atoms are in a line, we have this C infinity rotation. So then the only other symmetry element we need to look for is a C2 that is perpendicular to that. So if we have such a C2, the C2 would be an axis that would run through the molecule this way. And this rotation would take oxygen into oxygen, and it would rotate 1/2 of the carbon atom into itself. And notice that since we have a linear molecule, we can find an infinite number of these C2s, we just keep rotating around like this, and we'd have these axes moving around in a molecule like CO2. So therefore, since we know we have a C group and we have an infinite number of C2s that are perpendicular to our high order rotation axis, that tells us that we have a D group. So this is the group D infinity H. So we don't specifically have to look for the mirror, but there will be a mirror that's the high order rotation axis goes this way. So we have a mirror plane in this plane, which we do because it would reflect the oxygen at the left to the oxygen at the right. We have this point group D infinity H. For another example of a linear molecule, we can look at the very important organic compound acetylene. So acetylene has the following structure. So this is a 4-atom molecule. Again, because of the carbon-carbon triple bond, it's sp hybridized. We know that this is a linear molecule. We can also derive this fact that it's linear from the SEPR theory. So again, we know that along the axis of the molecule, the linear axis, that we have this C infinity rotation. And then the only other question is to look for C2s, at least one C2 that is perpendicular to that. And again, now we find a C2 axis, but the axis runs in between the two carbon atoms. So we have a C2 axis, but it doesn't run through an atom, it goes between two. But we notice that if I do a C2 rotation, it will take this carbon atom to that carbon atom, this hydrogen to that hydrogen. So in that case, it tells us that we have the point group D infinity H. And this is one of the two possible point group assignments that we can have whenever we have a linear molecule. So let's look for another linear molecule that does not belong to this point group. So let's find an example of the other group. And a classic example of the other point group is the compound carbon monoxide, one of the absolutely most important compounds in all of inorganic chemistry. We know that it has to be a linear molecule because it only has 2 atoms. There's no possible way to arrange 2 atoms in such a way that they are not linear. So whenever we have a diatomic molecule, it will fall into one of the 2 point groups, D infinity H, which we've already described, and the other possible point group, which we're going to talk about right now. So again, we notice along this linear axis, we have this C infinity rotation. But I noticed something, that I no longer have a C2. There's no, whether it goes through the carbon or in between the 2 atoms or through the oxygen, there is no C2 that is perpendicular to the high order rotation axis. So that tells me I don't have a D group. I have a group that must be a C infinity group of some type. And again, because we have a linear molecule, we notice that we can find a whole series of mirrors that cut through the molecule. This way there's an infinite number of these mirrors, but the mirrors include the rotational axis. And since they include the rotational axis, they are not horizontal mirrors. So therefore, the point group assignment in this case is the other possible group, which is C infinity V. So C infinity V for carbon monoxide. Recall that the other point group is D infinity H. So notice that the V goes with C and the H goes with D. There is no group C infinity H and there is no group D infinity V. So make sure you keep those distinct from each other because those are the only 2 possibilities. So let's look at another linear molecule and see if we can identify its point group symmetry. So we want to take a molecule that we looked at already, with acetylene, and now make a very small substitution in it and substitute one of the hydrogens with a chlorine atom. So now we have a chloroacetylene. And we want to assess its point group symmetry. The molecule is still linear. So here is our linear axis. And we notice that this particular axis, because it's linear, gives us a C infinity rotation. So you have C infinity there. And then we want to see if we have a C2 that is perpendicular to it. Well, if we put a C2 here, it would take carbon into carbon, but it would also take chlorine into hydrogen, which are not the same. So it shows us that now we do not have a C2. So this must be from the point group C infinity V. There's one last thing you want to watch out for and be very, very careful with. And that is this idea of linear molecules. So for example, we notice that we can represent acetylene, so we'll go back to acetylene again, one of our classic D infinity H molecules, and that in organic chemistry nomenclature and shorthand, we can often write it like this. So that's one way to write acetylene as a shorthand. We can also look at this particular molecule here, which is a butine. It's a butine because we have a triple bond. 4 carbons tells us that we have a but group of some type. So this is 2-butine. But if I write it as shorthand, I can write it like this. And when I write it like this, it might confuse me if I'm not paying attention completely to what this represents, because this looks linear. And we notice that this molecule, the carbon chain is linear, but then I have the sp3 hybridized carbons at the end, so that the hydrogens will be out of the line. So by having these methyl groups at the end, the hydrogen atoms, so let me kind of draw where the hydrogen atoms would be. At least one depiction, we can have 2 in the plane of the board, and then one's going to be sticking out towards us. So now we notice that none of these 3 hydrogen atoms is in the line of the carbons. So this molecule is not linear. So because it's not linear, there's no possible way it can be C infinity V or D infinity H. The linking between linear molecules and the point groups C infinity V and D infinity H is an if and only if. If it's linear, it's got to belong to those 2. If it belongs to those 2, it must be linear. I thank you for your attention. Don't forget to subscribe. Have a good one. Don't forget to subscribe. Have a good one.